afternoon, everybody. I hope everybody's having a wonderful day. So we're going to be picking up and discussing a bit more about set theory today. I'm going to revisit something I had said in a previous lecture, later talking about the idea of the universal set. And we might start talking about functions. So before anything, I thought I would take a little bit of a revisit to the idea of proving different set identities. So sometimes you might be posed with an idea, in particular an identity, and ask yourself if that identity is in fact true or false. Normally it is because somebody else already proved it, but imagine somebody posits something to you that looks something maybe like this. Like A set minus B union with B set minus C, and asking if that is equal to A set minus C. So somebody might ask you something like this: is this a true statement or is it false? So I wanted to talk a little bit about how you would maybe go about trying to determine if it's true or false. So I thought I would take a step back, so I'm just going to engage you with some ideas here. Just some general advice. So if you're trying to deal with proving these kind of statements, remember these are universal statements, because these have to be true for any sets, in particular the ones that we're interested in. And you have two possibilities. Either you try to prove the statement true. So you have to ask yourself two questions, and this is generally what you have been doing all this time. But at the same time, I really want to remind you of this, is when you look at a statement, you need to ask what needs to be proven and how are you going to do it. So the how is usually the hardest part of this, but you can't get to the how until you've identified the what. So don't forget that you always need to read a statement very carefully and see, does it make sense and what am I trying to do? So just keep that in mind. So that's one possibility. The other one is, of course, if you understand the statement, try to see if you can come up with a counter example. So remember, if I just have the counter example, this is just one example that shows that the original statement is in fact false for a particular case, for a very particular case. That means the whole universal statement must be false. So, just generally when you look at this, I make it sound really simple, but honestly, it is a process of trial and error a lot of the time. But I'm going to give you some ideas how maybe proceed with this. So just be prepared when you start playing around with some ideas to just start looking at what you're doing. So maybe decide on one of these just based on a hunch or your intuition. And then just be prepared to change strategies. If, say, for example, something you've discovered just kind of gives you a hint that maybe it should be the other way around, or maybe there's something you've demonstrated that actually says, hey, look, hold up. Maybe it is actually that it's the other possibility. So you got to be prepared to change strategies. Or for example, if you even are trying to prove a statement is true, and say one approach just does not work very well for you, try a different one. If, for example, trying to prove it directly isn't working very well for you, or at least isn't working nice, maybe try contradiction, if it makes sense to use it. But just be prepared to do this. So sometimes you might just sit there and you might try it several different times until you might get it, you might not. So that brings me to my example here. So I'm going to let A, B, and C be any sets. And then I'm going to ask this question. So it's A set minus B union B set minus C equal to A set minus C. Everybody gets it? So I just want to know if this equality is true or is it false. So if it's true, that means the equality has to be true for all sets A, B, and C. If it's false, then there has to exist some A, B, and C such that the equality doesn't hold. So those are kind of our two possibilities that we have to look at, because this statement is either true or false, right? So I'm looking at this, I don't know. Okay, we got A set minus B, we have B set minus C. Now, over there I have A set minus C. It looks kind of like something that might make sense, but remember, we have to remember what these definitions mean. If if I have A set minus B, okay, that means I remove all the elements that are related to B, right, from A. For B minus C here, I have to remove all the elements that are in C from B, right? See, I don't know. This could go either way. So here's one strategy I have. I'm going to try to see what their Venn diagrams look like, because I only have 3 sets I'm going to play around with. And I'm just going to assert and assume that the statement is actually false. So it means I just need to find 3 sets. There could be some 3 sets here, such that that's not going to hold. So I'm going to draw a Venn diagram. Now, it doesn't necessarily have to look like this Venn diagram. I'm just going to draw one where the 3 sets are not mutually or pairwise disjoint, meaning they overlap. So I'm going to draw 2 Venn diagrams, and maybe this is going to give us some intuition. Because remember, if that equality holds, then this means that no matter what A, B, and C are, I should end up with the same Venn diagram in both cases, right? So if I draw the left-hand side here as a Venn diagram, and I draw the right-hand side as a Venn diagram, they should match, no matter which sets I select. So I'm just going to pick this one, because I think it's kind of intuitive. So this is going to be my left-hand side here. So I have 3 sets here. I'm going to call that one A. I'll call this one B. And I'll call this one C. So remember I said that these are not pairwise disjoint. They all overlap. So let's take a look at this. Okay. So it's saying, on the left-hand side, I have A set minus B. Now, the way you would approach this, right, is I can look at A first, and I say, okay, A set minus B, right? A set minus B means that I'm going to remove all the elements from A that belong to B, right? So we know that nothing right here within these 2 regions here that are intersecting at these 2 spots, this one and this one, we know that there's nothing there, right? Because A set minus B would remove the elements that are related to B from A. So we know that it's somewhere here is not going to be what we're looking at up to this point. So that's what this will look like, right? Okay, how about B set minus C? Okay, B set minus C, however, that is where I give you B, and I remove all the elements that are from C, right? So I'm going to remove this one, right? And I'm going to remove this region of elements as well from B. So it means that we're going to end up with something kind of interesting here. Because I'm going to take the union of these 2 possibilities. So, just to make this a little easier to visualize, I'm just going to shade with a diagonal set of lines just to indicate the difference between them. And then we'll see what happens. Okay. So, if I have A set minus B, remember, that's all the elements that are in A but not in B. So I'm just going to shade A like this. Just so I can see one direction here. Okay, then the other one is B set minus C, right? So I got to remove all the elements that are from C from B. So I'm going to draw the dashes the other way. Okay. Well, look at that. Look at that. So so this is B set minus C. The dashes that are going this way are lines. The A set minus B, those are those lines. Now, remember, those are the results of each one of them separately. So when I take the union, I need to combine both shaded regions. So I end up with just So I should end up with something that looks like this. Now, I only have one color to work with here, unfortunately, so for some reason they're all gone. So I'm just going to, so this is A and that's B, remember that. So that's what the left-hand side looks like. Here's the right-hand side. This one's much easier, by the way. It's A, this is B, and this is C. Now keep in mind that technically this is a Venn diagram, so we would have the universe out there. Remember, the universe is just some set that contains all of these. Now, I'm going to talk more about that later, okay? So just remember, we talked about this the other day. Okay, A set minus C. Okay, well, that's just A, removing all the elements from C. That one's easy. It just looks like this. Well, look at that. Look. Look at these. They don't look the same, right? They're not the same Venn diagram. So this would immediately tell you, hey, look, probably this is false. Now, obviously, I can't, the burden on me is to say, hey, look, if I want to prove that this thing is actually false, I need to give you a counterexample. So the Venn diagram, I can actually use the Venn diagram to come up with a counterexample in this case. Now, it's convenient because I only have 3 sets I'm working with. If there are many more sets, you'd have to be a bit more careful. You might not necessarily want to use the Venn diagram approach. Instead, you might want to take and look at the statement directly and maybe manipulate it using set identities and see if you can get the other side. So I'm just going to give you an idea. So what I'm going to do is I'm going to label each region. I'm going to label each region of the Venn diagram. So this is basically what I'm going to follow. Remember, that's A, this is B, and this is C. I'm going to label it like this. Now, you don't have to label it like this. I'm just assigning numbers just to each region. I'm not picking any special way of labeling these. So the only thing is that each region has a distinct number. So this region here is just going to have 1, 2, 3, I'll call that one 4, 5, 6, 7. And now oftentimes, if you ever are dealing with operations involving the complement, you might need a region for outside of all of these. So you might want to number that, like say 8, because I have 8 different regions here. Because each set is each element is either in a set or it isn't, and I have 3 sets. So you can naturally figure out, okay, where did 8 come from? I'll let you think about that. So now just make sets A, B, and C to consist of each subregion. So I've just numbered the subregions here. And now all I'm just going to do is I'm going to construct my sets. So here's a counterexample. So I'm going to let A. Now, I'm going to look at my Venn diagram here. Okay, this one consists of regions 1, 2, 4, and 5. So that's what's going to be in A. B is going to be, let's see, we have 2, 3, 5, and 6. And lastly, what do we got in C? We got 4, 5, 6, and 7. Yes, very good. And now what I'm going to do is I'm just going to verify that I've indeed have a counterexample. So then, I'm just going to take apart what I have over there. So I'm going to start with a minus b. Okay, a minus b, well, what's that? Okay, we have 1, 2, 4, and 5. And we have 2, 3, 5, and 6. Now, notice that a, so b here has a 2 in it. It has a 5 in it. So notice that I need to remove 2 and 5 from a. And I end up with 1 and 4. B minus C, that is just simply, okay, well, C has 4, 5, 6, and 7. Notice that I have 2, 3, 5, 6. 5 and 6 are in C, so I need to remove those. So I got just 2, 3. And let's look at this. We have A minus B, we have B minus C, and then we also need to make sure we check A minus C. A minus C. Okay. C has 4, 5, 6, and 7 in it. This has 1, 2, 4, and 5. Okay, so notice that 4 and 5 are both in C, so I'm just going to have A minus C being just 1 and the elements 1 and 2 in the set. So I just end up with those, and I'm just going to put it all together. So A minus B union B minus C is equal to the union of the set containing numbers 1, 4, union, and remember B minus C is 2, 3. 2, 3, which this is equal to 1, 2, 3, 4. Isn't that cute? We've got the set 1, 2, 3, and 4 as its elements. However, A minus C is just the set with 2 elements, 1 and 2 in it, right? So this, however, is I'm running out of space here. But just imagine I kind of bring this around. This is not equal 1, 2. Thus, A minus B union B minus C is not equal to A minus C. And I've done my counterexample, so I verified that indeed it works. So this is one way you could do it. So you could start off by just checking their Venn diagrams, assuming there's only a small number of sets. This won't this will not be very won't be a very effective strategy if you have a lot of sets to work with. You might take more of an identity-based approach. Or you might need to be very clever. Just like I'm going to do here now. Okay, so instead of creating this, I could have actually just been a little bit more crafty. So remember, I want to show that A minus B union B minus C is not equal to A minus C. Because I know that for certain it's false. But it means I can do better. So notice that both of these here are B. But it also looks kind of like I have something that I can get. I would like to have it so that the left-hand side has an element in it. And the right-hand side does not have anything in it. So maybe there's a way I can do that. Well, notice if I make A the empty set, if I take the empty set and I take the difference with something with an element in it, I'll just get the empty set, right? But if this right here was just something with some element in it, and C was, say, the empty set, there'll just be some element with something in it, right? But on the right-hand side, you'll notice that I have A minus C. If they're both the empty set, then I'm just not removing any elements, right? Just empty set. Removing all the elements from the other empty set. So let's try this. Usually when we're trying to disprove claims, we try to come up with the simplest or minimal counterexample so that you can really convince somebody that say, hey, look, what you said is actually false. Here's a very cute example why. And so here's a simpler counterexample. So oftentimes, mathematicians take great pride in finding very simple counterexamples to things for several reasons. One, it's one way you can tell your friends, hey, look, rather than this big complicated thing, which sometimes does happen in the literature, you sometimes have a counterexample that's so unintuitive to follow that some people will just like, okay, they disproved it, what does it tell me? Oftentimes, if you get a nice simple counterexample, it tells you something a little bit about what you're giving in the first place. So here's a simpler counterexample. I'm just going to use that idea. I'm going to let A be the empty set. B is going to be the set containing the number 3. Why the number 3? I just feel like it. And C is going to be the empty set. Then A minus B, remember A is the empty set, so this is just the empty set. B minus C, okay, well B is just 3, right? There's just an element with one element, the number 3, minus the empty set. Okay, well that's just the set containing the number 3. And the set difference of A and C is equal to, of course, this is just the empty set, that's the empty set. Okay, well, there's no elements for me to remove as I obliterate the chalk. That's where it's at. So, that just means, notice that A set minus B union B set minus C is going to be equal to the empty set union the element 3, which is, of course, just the set containing the element 3. Which is, of course, not equal to the empty set. Which is just, that's that one right there. Therefore, A minus B union B minus C is not equal to A minus C. See that nicer counterexample? So I ultimately tried to expose a problem with this relationship by observing carefully properties about set differences here. So sometimes you start off with something that looks a little bit more complicated as a counterexample. Then you can find maybe a more clever way of coming about it. But you notice the way I did this one was I didn't actually use this idea. Instead, I used a different idea. I just used the definition of set difference to come up with the intuition I had. So that's basically some ideas you can take for disproving universal statements. Now, just for the sake of completeness, yesterday I gave you a list of identities. I'm going to show you one example of how you can prove a claim using set identities, just for the sake of completeness. You're going to look look like algebraic proofs, but I assure you they're not technically algebraic proofs. I'm just using equivalences between different set relations, these set identities, because they're holding over equality. So here's a claim. So in the assignment, I'm not going to ask you to do this, but I want to show you just because I think it's very important to see at least one. So I'm going to check if, given any three sets A, B, and C, A union B set minus C is equal to A minus C union B minus C. So I'm going to try proving this. So I'm going to prove the claim. So let's do a proof. So here's a proof. So what we're going to do is I'm just going to let A, B, and C be any sets. Then I'm going to start off with the left-hand side. I'm going to show the right-hand side. I'm going to do it over here because I'm just going to have one long chain of qualities, one coming after the other using identities. It'll look quite familiar to you because of the parallel I showed you last class. So this will remind you a lot of when we were doing direct proofs using logical equivalences. You also might be familiar with this idea when you do manipulations with algebra. It'll look quite similar. Well, A union B is minus C. Now, okay. Remember that anything I have as a set difference, I can always rewrite using the complement in the following way. So I have A union B. I can replace any set difference with intersection and then complementing the right-hand term here. So I can rewrite this as C complement. Usually it's a good idea to let the reader know what you're doing. So this is the set difference law. I wrote that on the board actually last class. Well, one of our last discussions here. So this, of course, if I look at this, I'm just going to permute these two. I'm just going to rearrange them. Just going to switch them around. So I end up with C complement intersect A union B. So I'm just using the commutative law. The commutative law. Then I'm going to use the distributive law. Remember, we proved that one in our last session. C complement intersect A union C complement intersect B. So this is just the distributive law. The distributive law. Then I'm just going to do I'm just going to commute a little bit. So I'm going to commute each one of these. So I want to write it a little bit differently in each one of these. I'm just going to permute them inside of each parenthesis. So A intersection C complement union B intersection C complement. So this is me just using the commutative law again. This is just the commutative law. Then, okay, well, look at this. Okay, notice this right here is just the definition for a set difference, right? I could rewrite this as a set difference. Likewise, I can use a set difference here as well. So I'm just going to transfer those back into forms that we're familiar with from earlier. So I'm just going to make that A minus C union B minus C. So this is just, of course, the set difference law. I'm just using it again. So the set difference law. is equal to A minus C union B minus C. And we're done. That sure looks like a lot less words. It's because I'm just using set identities. So I'm just moving between different identities. Each one is equivalent to each other's previous one in the solid chain. So, that being said, I just want to show you an example of that. Now, I'm going to do a few more things with you here today. Now, the other day I introduced the idea of the power set. The power set, if I give you some set X, the power set, by definition, is the set given X. It is actually the set of all possible subsets of that set X. And I gave you this idea at the very end. Thought I would prove it for you, seeing as you have all the tools to do so. For every, now I'm going to write my integers a little bit of a different way because now I have a bit of set theory I can play around with. Before I used to just say, oh, like I used to write this in somewhat of a different way. But now since we've seen union, I'm going to write this a little bit differently. You don't have to do it this way. This is just one way. I just want to show you many different ways I could write the same thing. So for every non-negative integer, which is just going to be the set of positive integers, union 0, if the cardinality of a set X is equal to n, then the cardinality of the power set of X is equal to 2 to the power of n. That's what I'm going to prove for you right now. We're going to use mathematical induction to do this, but I've noticed I've never really shown you an induction proof that involves objects other than numbers typically. Numbers are algebraic identities or sequences. I want to show you one that involves sets. Well, sets explicitly. So I'm just going to do what I usually do. So consider any set X, because remember, X can be arbitrary here, right? Technically, even if I want to be more precise, I could mention that up at the top. But remember, I only really care about the size of the set. So consider any set X for every n greater or equal to 0. Remember, n is an integer here, but it's just greater or equal to 0. Let S of n denote the statement S of n, and it says if the cardinality of X is equal to n, then the cardinality of the power set of X is equal to 2 to the power of n. So you're going to notice that I'm going to be performing my induction on the size of the set. So I'm inducting on n. So when I say inducting, normally you try to find a part or structure in the statement that you can perform the induction on. So in this case, it's very natural to look at n, because n is both on the left, it's a part of my hypothesis, and it's also a part of this equation right here that I want to prove. So I start off as usual, I go base step. So I'm going to try showing this for n is equal to 0. To show S of 0 is true, we must show must show that if the cardinality of x is equal to 0. So just as a reminder, remember cardinality, I'm just talking about the number of elements in the set. So we defined this much earlier on in the course. If the cardinality of x is equal to 0, I was just randomly thinking to myself, I didn't mention it earlier, that if the cardinality of x is equal to 0, then the cardinality of the power set of x is equal to 2 to the power of 0, right? That's what I ultimately need to show for s of 0. I'm just going to continue the base step up here. Sometimes when you're dealing with these somewhat more complicated statements, I want to make sure I state what I'm going to do. So, let's notice that the only set with cardinality of x equal to 0 is, there's only one, right? It's just the empty set. Is the empty set. Is the empty set. So, is the empty set. And the only subset of the empty set is itself. The empty set. Right, remember that we talked about that if I give you a set A, that A is a subset of A, right? Remember, the empty set has no elements in it, but however, the only subset of it is in fact the empty set. Just in this by the exact same extension. So, hence, there is only one subset of x, and the cardinality of the power set of x is equal to 1. Notice that I'm talking about the left-hand side here. So you'll see that I just got the left-hand side. So this part right here I've received. So I know that that is equal to 1. Now I'm just going to look at the right-hand side. The right-hand side of s of 0 is 2 to the power of 0, which equals 1. So both sides of the equation, in s of 0 are equal. And s of 0 is true, right? So we're seeing that I needed a little bit more machinery to get this working right. So all I did was I just showed s of 0 was true. Naturally, I need to do the inductive step. So remember that I'm just going to use my weak induction, or just mi. So we have the inductive step. We're going to do what I usually do. Fix sum k greater or equal to 0. Ooh, that was bad. Hopefully you guys didn't get that on camera. Oh, that was bad. I apologize. Whew. assume that S of k, so remember this is just if the cardinality of x equals k, then the cardinality of the power set of x is equal to the power of k. To the power of k. We'll finish it up here. Okay. So we're just going to assume that's true. We need to prove that, remember I just need to state what I'm going to prove, S of k plus 1, remember this is just if cardinality of x is equal to k plus 1, then the cardinality of the power set of x is equal to 2 to the power of k plus 1. I want to show that this follows. So, what are we going to do? I want to look at this very carefully. I'm going to come back to this idea. First, I'm just going to consider any set, because remember, x right now has cardinality of k plus 1. So I'm just going to say that, right? Let x be a set with k plus 1 elements. With k plus 1 elements in it. Now, I want you to observe that k plus 1 is greater than or equal to 1. That means that there's at least one element I can use. So I'm just going to use this. You're going to see why. As k plus 1 is greater or equal to 1, select any element z in the set X. So I want you to observe something that's really neat here. If I were to take Z, and then I considered the subset without Z in it, then you'll notice that I've removed one element from my set, but there's two possibilities for its possible subsets. There is the case for which Z is not a part of the subset, or Z is a part of the subset. So if I consider any arbitrary subset of X, either it does not contain Z or it contains Z. I'm going to show you that you can actually pair up the subsets, line them up, and then you could count them, and we could use the inductive hypothesis. So here's the idea. Observe that any subset of X either contains Z or it does not. Furthermore, any subset, I'm going to give it a name, I'll call it A, any subset A that does not contain subset is a subset of x set minus z. I think that's a good place to stop for the sentence. See, I like to come up with these together. It's hard doing it by myself. So, that being said, you'll notice that any subset A, it will not, if it doesn't have z in it, then it must be a subset of x set minus z. So remember, that's the set with z in it. So what I'm going to do is I'm going to pick out some subset from this, and I'll show you that you can actually create another subset that actually has z in it, and show you that actually you could actually pair them up quite nicely. You'll see what I mean. So here we go. The drama is just killing me here. So notice that for any such A, remember I'm talking about the subset that doesn't contain Z, any such A, there is another, there is another subset. There is another subset, B, which is just going to be equal to A union Z, a subset, ooh, that was kind of bad, a subset of X containing Z. If you're wondering why I'm just taking that all in at once. I hope you're enjoying this. Containing Z. I'm not the biggest fan of chalkboards, as you probably can tell. That being said, you'll notice that for any A, I've shown you that you could give another subset B that contains Z in it. So for any subset such A, remember A has one less element than X did. At most, right? So like, if remember A is any subset, it could technically only have like one element in it. It could have two, or something like that. So I'm just showing you that for any subset, I can create one where Z's in it by just using union. Consequently, any subset A can be matched up with a subset B. Any subset B. So I've shown you for each A I could get a B. And remember, I'm not losing any elements. There's nothing that's hiding here. Because remember, I considered every subset where Z isn't present. So remember, any subset follows this in terms of being a subset of that. So it's either there or it isn't. For any one that is a subset of this, I can create one where Z is present by taking the union of a set containing Z. So it means I'm not losing any elements when I do this. So what do I end up with? Let's take a look. Thus, there are twice as many subsets of X as there are subsets of X set minus Z that is, so I've just given you the entire relationship for the left-hand side. That is, the cardinality of the power set of X is going to be equal to 2 times the cardinality of the power set of the set X set minus Z. So I've shown you a nice recipe. So every time I put in another element, I end up doubling the number of elements there are. So if I start off with one element, if I take this idea, if I introduce another element in, I double the number. Likewise, if I take that set, I just double the number every single time. So I'm just showing you one approach to getting this. There are other ways you can derive the same argument using combinatorial arguments. In fact, this one is actually secretly a so-called combinatorial argument. I haven't really talked so much about those quite yet. So basically the idea is I give you one set, I show you how you can create another set without losing any elements, so I'm just counting them. I've done something like this in the past when we were talking about proving the very basic series for the arithmetic series. I noticed, remember I drew that all those rectangles and I drew some boxes and I said, oh, I could pair up each one with the other one. And ended up getting half the count when I paired them up. This is a very similar idea. So now I have this to play around with. So let's do this. Okay. So let's finish up the proof because we're just about there. As the cardinality of X minus the set containing the element Z is equal to K. Remember that, I just removed one element. Beginning at the left-hand side of S of K plus 1. The power set of X. I'm going to take the cardinality of this. Remember, I derived this right up here. I got 2 times the cardinality of the power set of X minus the set containing the element Z. Then, here we go. Okay, what's this? What's this? Well, that's the set. That's a set with K elements in it, right? But what we actually have that, right? That's just the inductive hypothesis. So let's just put that in. 2 times 2 to the power of K. So this is by the inductive hypothesis, S of K. And now I'm just going to multiply this out, and notice that since they have the same base, remember this is just 2 to the power of 1. I end up with 2 to the power of K plus 1. Which equals the right-hand side of S of K plus 1 and S of K plus 1 follows. So we've completed the inductive step, and now I just need my final conclusion. So it seems like we're probably not going to get to functions today. I'm just going to talk about one more thing right after I finish this proof. Remember, we always need our conclusion. Therefore, by the principle of mathematical induction, MI, S of n is true for all and in the set of all positive integers, union 0. Basically, all the non-negative integers. Sorry, the chalk has still got me shaking. Okay, so that completes that proof. So I really wanted to show you that, so you actually have an example of an inductive proof that isn't just, oh, I put the numbers in, I just do some algebra. This one requires a little bit more thought, right? So I want to talk about something a little different.